Hi, good evening and welcome to the ZP Developer Zone webinar. So the date I've got this is the 1st of September 2024. I have started to actually do these on a Saturday evening, but I always intend to actually do them on a Sunday morning. But that said, it's easier to go now. This is being recorded and it's being essentially recorded live, so I'll just go through the questions. So the ZP Developer Zone is really a way of answering technical questions. And sometimes the questions are commercial, but there's a sort of lot of technical, let's say, wrapped up in them. And so tonight I'll be talking about cyclic voltammetry and screen printed electrodes. To be fair, this question I found it on ResearchGate and I thought it was kind of interesting, and I thought it definitely fitted with the themes that we like to cover in the ZP Developer Zone. So I will cover cyclic voltammetry. It's on a third party. It's not on our screen printed electrodes. So at Zimmer & Peacock we manufacture a lot of screen printed carbon electrodes. This is just one of the let's say architectures we have, but we do have other ones, and the person's really worried, not really worried, but they're wondering whether they have a reversible system because they have a peak-to-peak separation of 400 millivolts. I'll basically say that I think you do have a reversible system. You don't have a reversible system on that carbon electrode because I think it's in part blocked by organic binders that are in the ink, but I will also show you a procedure where you can actually essentially burn them off or chemically remove them, and let's talk about that when I get to your slides. Question number 2, this is a, if you are a ZP customer and this person or client, and this person is using our gold electrodes, then we will offer help. And so this, when I say help, this person has some problems. It's a little bit tricky actually, because they're first of all saying they had a problem with reproducibility. I have a suspicion they actually have a problem with binding. So a lot of people use gold screen printed electrodes. They want to form self-assemble monolayers. I've got a suspicion they're having a problem binding to the gold. Now I've asked them to see the paper that they're actually following, because there's something not right. I mean, we, at Zimmer & Peacock, we do a lot of contract development, contract manufacturing. The reason we produce such good, electrodes it's because in fact we use them in our programs and in our clients' programs. It's a very unusual business model. Anyway, that said, I will be answering a question on gold screen printed electrodes this evening. Also, this is a nice one. It came in, somebody sent me a very nice set of slides talking about CGM, continuous glucose monitoring. I've got a really strong suspicion that your problem with your signals may actually even be corrosion of their microneedles, and I will discuss that in a minute. I suppose it's probably worth saying at ZP we do have a lot of experience with microneedles. I'm also going to say that microneedles and wearable microneedles is a very expensive technology to get into and a very expensive technology to do well. This watch, for example, ZP owns the IP on this, but it got 20 million euros worth of investment in this microneedle watch. It's not finished yet, and it's actually got 50 patents behind it. So it's probably just worth saying that microneedles is not a low-cost technology to get into and do well. The other company in this microneedle space is actually a company called BioLink, and they've spent 158 million US dollars in the last 4 years. Anyway, we will cover CGM, continuous glucose monitoring, microneedles, and very shortly. First two questions are about screen printed electrodes, and then the fourth question here is actually about screen printed electrodes. This is a simple enough question, which is whether our screen printed electrodes are reusable. And I'm going to answer the question by giving you a couple of examples. In one example, the answer is yes, and the other example, the question is no. And that is a common thing. This is the world of electrochemistry and chemistry and biology. So whether something is reusable, it really depends on what actually the person is putting onto those screen printed electrodes. Strong acids, strong bases, strong organic solvents, then yeah, that's going to be a problem. pH 7.4, ferricyanide type solutions, sure, they can reuse them as much as they want. So whether a screen printed electrode is reusable really depends on what you're going to use it for or use it with, and I'll show you a couple of examples. The last one here, actually the fifth question here is, somebody sent me a paper. They're really in the paper describing a chemiresistor. They've got a couple of wires. They've got an ink between those wires. There's a volatile organic compound, and the volatile organic compounds affect the resistance, and they're wanting to know whether ZP can do a custom, let's say, fabrication. the way that the device is described in the paper, it's not scalable. It's not something you can really manufacture. I'm going to describe that you should actually take some of our, for example, Hypervalue carbon electrodes like this, formulate the ink from the paper and just drop cast it onto this, and that's how you'll actually end up making those chemiresistors. Question number 6, a long-time friend to the company is interested in purines, pH, hormones and nitrate. Actually, a lot of questions that are coming in tonight are actually coming in about potentiostats. So people are very interested in, there's a particular brand of potentiostat out there. It's been around, for 20 odd years. It was set up by the father of the current guys. Now, I will, obviously at ZP, we do make a potentiostat. This is the Sensi-All potentiostat. In fact, if I want to do square wave voltammetry, I can do square wave voltammetry. Device is connected, so yeah, it's already Bluetooth. So we do a potentiostat. So as we go forward, I'll be more and more keen to actually support screen printed electrodes from Zimmer and Peacock with Zimmer and Peacock potentiostats, because then I know that they'll work together. In fact, some of the questions that are going to come around, especially in question number something like 8 in a minute, I'll highlight it then. Question number 7 is a tricky one because somebody wants to make a well plate that can do ethanol detection, and they probably want to have anti-fouling coatings involved in that. It's probably worth saying that we've got a lot of experience in biofouling, unfortunately. Anyone who works on CGM, this is an example of CGM, continuous glucose monitoring. In fact, I realize I have to share my screen in a minute to show you the question, but something like this is the Abbott Freestyle Libre 2. They'll have a problem, not a problem, but they will suffer from biofouling. So biofouling in biological systems is not unusual, and we see it across several applications. So sorry, I should have gone back to the questions. So I will talk about question number 4, which is somebody's interested in our Hypervalue carbon electrodes, whether they can reuse them or not. Question number 5, somebody wants to make a chemiresistor for volatile organic compounds. You can actually use the Hypervalue carbon electrodes to do that. Question number 6 will involve a discussion on the Sensi-All platform. In fact, very soon in September, I'm going to have a conversation with an academic group in the UK that have been using the purine sensors actually in a clinical trial. So we will see the results of that clinical trial shortly. But they're interested in nitrate, hormones, pH and purines. And actually we do have all those on the Sensi-All platform. Like I say, question number 7, the person wants to both measure alcohol or ethanol rather in 96 wells and also have an anti or biofouling coating. That I think is a significant program. It's not just something, when I say significant program, programs like that end up costing more than 100,000 or more, like in the range 250 to 500,000. Those are large complex programs. Question number 8, I'm not discussing, they want to use ZP screen printed electrodes with a third-party potentiostat. The third-party potentiostat that you're interested in actually has a compliance potential problem. So our screen printed electrodes are particularly good at solving that compliance potential problem, or that compliance voltage problem. If you're not sure what compliance voltage is, please go onto our YouTube channel, because I did do a video in the last couple of weeks about compliance voltage. So yeah, you're welcome to use our screen printed electrodes on the third party, but I can't support that if it doesn't work the way it's meant to. By the way, question number 3, they are also using a potentiostat that does have a sort of known compliance potential issue as well. I will just share. So of course I'm much more keen that people don't use, in question number 8, use the third-party potentiostat, but of course I'm also, because I'm also a manufacturer of potentiostats, this is the, in fact, if I was going to do what they were going to do, I could quite easily do it on this particular potentiostat, especially as they're probably going to end up doing things like immunoassays. So if they're going to do immunoassays, square wave voltammetry is a good technique. If they're also EIS, electrochemical impedance spectroscopy, would also be a good technique as well. That said, let me go back to the screen. Just to say, we've got some upcoming webinars coming up pretty soon. I'll go quick. If you are interested in any way commercializing point of care, point of need diagnostics or devices or biosensors, please come to this webinar on the 24th of September. So you've got plenty of time to clear the calendar. We do one in the morning, one in the afternoon. The one in the morning is useful for colleagues in Asia, and the one in the afternoon is useful for colleagues in the Americas. If you're interested in wearables, yeah, so somebody, for example, is interested in continuous glucose monitoring, then it's probably worth coming to our wearables. I put the 28th of August here. I realised there is another one. That link will take you to the most recent one. I've definitely put another one in the calendar. So if you're interested in wearables, it's not on the 20th of August, that's actually happened, but click the link and it will hopefully take you to the next upcoming one. If you're in academia, especially sort of questioner number 1, for example, is kind of using a third-party screen printed electrode. I think they're really going to run into problems pretty soon. It's actually not about whether their peak-to-peak separation is 57 millivolts per electron or 59 millivolts per electron. It's actually going to be about reproducibility of electrode. I think they're already going to start suffering from the reproducibility of those electrodes, so it's worth coming along to this webinar to kind of get a deeper dive on that. Just a quick promotion from ZP, just to say, look, we do have a lot of screen printed electrodes. There's a lot of discussion this evening about screen printed electrodes. I think only possibly one other question is actually a ZP client. We will troubleshoot other people's screen printed electrodes, but it makes it tricky because you can't criticize other people's material, and you don't always, well, we don't always know what is going on in their manufacturing. I can speculate, I can give you fixes, but of course it does help if you're actually using ZP screen printed electrodes. So any links that I put up, they'll also appear underneath the YouTube video as well. So thank you so much for sharing this. I was kind of, I'm not on ResearchGate, but actually, to be fair, it is actually quite interesting on occasions. Somebody was kind enough to share this voltammetry. There's lots of nice things about this voltammetry, actually. I mean, it's a, you know, it looks quite classical. In fact, I can see that, yeah, I can see a resistance problem when I look at this data now, actually. It's the, you know, it's nicely shaped. They have a lot of current. I'm kind of surprised by how much current they have, but there we go. I'm not going to call out what screen printed electrode this is. It wouldn't. I don't think it would be super professional of me, but it's not one of our screen printed electrodes. It's a third-party screen printed electrodes, they're most concerned that actually their peak-to-peak separation is quite high. They do call out the conditions when they do this in the next slide. In fact, one of the things I would say is, I do believe that fundamentally this is a reversible reduction and oxidation. I mean, you've put it in your notes, you know, it's because it's ferricyanide. You know, there's a body of literature that says, you know, when ferricyanide is done on a more pristine electrode, let's say, then you will get lots of characteristics indicative that this is a reversible. Now, reversible, you're asking if this is reversible in terms of thermodynamic reversibility. This raw data would say that it wasn't. I got a suspicion that the surface is somewhat clogged, blocked by non-conducting material. So when they make these inks, they have carbon in there, it's conductive, or graphite in there, but they also have binders. I got a suspicion that there's a quite high density of binders on the surface, which is basically increasing your RCT, or charge transfer resistance, and making the system therefore appear that it's not actually reversible, when I believe it strongly is actually reversible. If I was doing this experiment, what I'd be doing is I'd be first of all recording the background. So I would just be running this in buffer. So let's say your buffer was PBS, phosphate buffer solution at pH 7.4. I'd run the buffer, and then I would actually add in enough ferricyanide to make that sort of 3 molar. And in fact, I'll just go back, and then doing that and just comparing that versus the buffer. But I have a super strong suspicion. I mean, sorry to say, what else is this? You know, if you want to kind of run a logical sequence, the logical sequence is run the buffer, then add the ferricyanide, let it dissolve, and then record that. And of course, there will be a massive increase because the buffer will have not much electrochemical activity. Just one comment, you don't necessarily have to go to quite these extremes. I see here you're going to -1 volt and plus, maybe plus 0.9 volts. In fact, if I look at your data, you know, everything interesting has actually happened in the window. I think you'll see in our data that we go from like minus 0.5 to about 0.5 volts, maybe with you up to 0.6 volts. You didn't have to quite go as high. In fact, you went up to 1 volt. So I don't quite think you need to do that. That could give you a bit of a problem because you're kind of putting a lot of power through that electrode that you wouldn't have otherwise had to have done. Power is equal to voltage times current. So you're kind of putting voltage and an associated current through onto that electrode and current through that electrode that you didn't otherwise have to have done, but it's no big deal. I do understand your concern, especially maybe if this is one of the more sort of when you're more, if this is something quite new to you, you're expecting 57 millivolts, but you're not quite getting 57 millivolts. I'll show you a trick in a few slides that you can actually get closer to 57 millivolts. The reason that I'm using the reason I'm saying 57 millivolts here is because the sort of Nernst equation behind this, you can either do it log the chemical concentrations or log to the base 10 of the chemical concentration, or you can use natural log. When they use natural log, it's 57. When they use log to the base 10, it's 59. But it's really a little trivial sort of matter here. Your cathodic and anodic peaks have a ratio of almost 1-to-1. So I mean, you know, I do believe this is a reversible system, but I do believe your electrodes have a slightly resistive surface to them. It's not super unusual. It is something that we mostly can avoid, and I'll try and show you a trick. Also, you can improve the situation slightly by maybe actually doing at a lower scan rate as well. So you've got 100 millivolts per second, and I'll comment upon that. This is some data from ZP. I don't know why I put a picture of I put a picture of a gold electrode up here. Probably just tiredness and trying to get to a deadline, let's say. But I actually think this data was actually for carbon electrode. That said, we're not perfect either. I mean, I think the peak-to-peak separation in this particular one was more like approximately 150 millivolts, which is better than the 400 millivolts. But I'll talk about how to improve that. In fact, I talk about how to improve it here. In fact, first of all, I want to say that if you go down to something like 10 millivolts per second or 20 millivolts per second or maybe 50 millivolts per second, you could improve your situation. The reason I bring this up is you don't have a problem called IR drop. IR drop is actually associated with the solution resistance. But I think you may have resistances due to organic material on those electrodes that's actually increasing the charge transfer resistance. It's not an IR drop problem. But how can you improve the situation? By the way, this is data of Zimmer and Peacock's electrodes. So you can see that at 10 millivolts per second, we do get a closer to expectation peak-to-peak separation. And we get also the kind of ratio between peak currents of about 1-to-1 that you would otherwise expect. This is I'll give you a link to this. This is some conditions on how you could potentially activate or clean your carbon surface. This is something that we could do on a ZP electrode. I've not tried it. You are dealing with somebody else's electrodes. I'm trying to give you some reassurance that it looks good. In fact, in the fact that I think this is generally a reversible system, but there's a film or a coating left on that screen-printed electrode from its manufacturing that's increasing your charge transfer resistance. You can try this method, but I have not tried it on your electrodes. So if you fry the electrodes or something goes wrong, unfortunately you do have to carry that risk. It's something that we've done on our electrodes, and I will give you a link there. So first of all, you were concerned. I'm not concerned that it's not reversible. I do think that actually the working electrode and probably the counter electrode actually do have some organic insulating material, and you could possibly take it off by this quite aggressive sort of cleaning method that I suggest here. Also, come to our webinar on the 25th of September. I think you're going to have a problem. You're going to have a problem, and your problem is going to be one of reproducibility. That when you use otherwise the same solution on different electrodes, you're going to find yourself with different peak heights, and you're going to get pretty annoyed, and it's actually down to reproducibility. So please come to our webinar on the 25th of September. There's one in the morning that should suit your time zone just real fine. Question number 2. This one gave me some concerns because first of all, I got an email to say I'm not getting reproducibility on your gold electrodes. Hey, this is Zimmer and Peacock. We do support our technology like I am now. Saying, okay, send me some slides. When I did dig into it a little bit, I found all these dates and times. It's probably just worth saying as well, this person's giving us some teaching here actually, that the person before was using a window on that ferricyanide experiment of like -1 volt to +1 volt. This person's actually narrowed that window down a little bit, which is probably a sort of more sensible thing to be doing. So you can take essentially some learning from this. I'm just gonna so you can still see that a little bit better. And it's on one of our gold electrodes. I was a bit concerned because I didn't like the reproducibility that we were having here. But digging into it a little bit more, I find out it's really May is the outlier. And I think once I started taking out, not taking out, I wasn't trying to be selective, but in June they were having some really good reproducibility, and I sort of I got told then later on an email they're actually doing different experiments, so it is hard to get reproducibility between experiments if the solution is changing. So now it's interesting because people will approach us with a problem, but the problem actually seems to be that it's not so much reproducibility. What they're trying to do, I suspect, is form a layer of biological material upon this electrode. So they take an electrode, and the electrode has a good cyclic voltammogram. They're probably investigating it with essentially ferricyanide. Then they try to put a coating on that surface, or that gold surface, and actually the electrode looks really just the same. If anything, it looks a little bit cleaner. So they haven't exactly coated it. They've actually just ended up cleaning the electrode or changing the electrode surface, maybe roughening it up a bit. So sometimes, this is in this example, it was a reproducibility problem. Actually, then you find out the solutions are quite variable. We're not looking at apples here. We're looking at apples and oranges and some pears. And then we actually found out the problem is actually this functionalization step where they're trying to put some macromolecules on the surface. So I've asked them to send me the paper, and I think this story will continue. But it is an example that if somebody's genuinely using our screen printed electrode technology, we can see, let's say, what's going on and give people advice. This one is nice. I'll go quite quickly on it. They're using microneedles to develop a CGM sensor. I got a very strong suspicion that most of what they're seeing is actually corrosion, and I'll dig into that a little bit. First thing to say though is I do appreciate the professionalism when people actually give us, and they have in this particular case, they gave us a series of slides, really laid out the story. There's nothing worse than I've got a problem and here's one line email on it, or I've got a problem and here's a one screenshot. Here actually people have sent a slide deck, so that was really appreciated. So part of the problem is they're going to actually end up with is I got a super suspicion that they're probably compliance voltage. It's not potential in this term, it's compliance voltage problem. So they're using a particular potentiostat that I think is actually with the amount of current that they are passing in these experiments, I have a horrible suspicion that they're compliance voltage limited. I just want to say that when Zimmer and Peacock is talking about testing of microneedles in glucose experiments, he says putting on his $20 million 50 patent protected CGM sensor onto his wrist. We do know what we're talking about. This is a similar experiment to the one that's shown on the left is shown on the right, except the one on the right is done at Zimmer and Peacock. So we do understand the kind of setup, and we do understand the pain and of these kind of experiments. So we're talking about continuous glucose monitoring. The first thing is, great set of slides, but you're really not showing me the raw signal. What you are showing me is an extraction from the raw signal. In this case, you've extracted current, and you're showing me current versus sort of glucose concentration. But in fact, that's an extraction. Below there's actually raw signal. So I'm going to show you some raw signal from Zimmer Peacock, and I'm going to say you need to generate raw signal that looks like this, then you can bring the microneedles back into this. I've got a horrible suspicion these microneedles are actually just corroding like crazy. But something's going on here. So I get what we're looking at here is signal, call it current, versus concentration, same here as well. But it is very hard to actually, it's kind of, I get the point, that you're talking here about current versus concentration, but your current is really high. It could be linked to your surface area of your electrode, but I got it. And if your current really is that high, I'm not sure that the potentiostat that you've got is able to really apply the compliance voltage that you would need to support this current. So I'm super suspicious that you're really seeing anything here. And if you are passing those kind of currents, I'm not sure that the potentiostat that you're using is actually good enough for the experiment. And if you are passing these kind of currents, this cannot translate to be a CGM, a continuous glucose monitor. It's quite a deep, it's not hard, but there's a deep dive here. But current means molecules. So you're passing currents here. That means that you're essentially consuming so many glucose molecules that if I was to put it onto the human skin, you would have consumed all the glucose molecules in the vicinity of that sensor very quickly. So, but I definitely don't think you are actually consuming glucose. I think you've got some active material associated with that gold or underneath that gold, and you're just corroding it because you're applying 650 millivolts to it. Your currents are too high. You need to step back actually and get a glucose experiment working. So this is the kind of, when I said you're not showing me raw signal, you're showing me an extraction of raw signal. This will be the kind of raw signal that, if Zimmer Peacock was testing a glucose sensor, we call it a staircase experiment, where here, and in fact I'll get Andre, and I really respect Andre. He is just setting up quite a simple experiment with one of our CGM sensors, but it's based on a screen printed electrode. So it's more like a planar CGM. It's not a microneedle in the same vein that this is a microneedle. I'll just flip this out. So if I flip this out, there's a very expensive to produce microneedle system here. But Andre is setting up a sort of lower cost CGM type experiment here, and he's going to put those sensors into that solution. I'm going to fast forward him a little bit here because he's talking about the setup. You kind of need to do this experiment and get this data before you then bring your microneedles in, because you have to baseline yourself and say, is this rig even really working? So this was actually a live demo that Andre was doing for a client. First thing he's done here is he's got, and he is using 650 millivolts, so similar to yours. He's just baselining himself here with 0 PBS. It's probably worth noting the kind of current that he's got. He's got, you had hundreds, if not maybe up to hundreds of microamps. Poor old Andre here, he's got like 0.2 microamps, 200 nanoamps. I could accept you would get hundreds of nanoamps, but the kind of currents you're getting, no, this is something else. So here he is, he's letting this sensor settle, and then he's going to add in a bit of glucose. I think he waits for about 100 seconds. Here he goes, so we're getting it close now. And then he adds it in to the beaker, and I'll describe this, and bang, there you go. You get a beautiful rise. You need to get to this position on something like our planar CGM sensors before you actually start troubleshooting those microneedles. I've got a suspicion that they're doing electrochemistry that other than just glucose. So Andre lets this run, and then he just adds in a bit more glucose just here. He just pipettes it in. I'll give you a link to this video as well. So you need to be able to repeat this experiment several times and convince yourself that your setup is good before you then, because if you can get all this working, that baselined you before you bring in the trouble of actually the microneedle setup. He does it quite a few times, and I will put a link to that YouTube video underneath this video. So your microneedles have come from a third party. Your currents are exceptionally high. If your currents are exceptionally that high, I'm going to talk about oxygen limitation in a little bit, but I actually think you've got a corrosion problem. You can see your currents versus our currents, and it's not just about surface area there. You've got something else going on. You need to be able to repeat Andre's experiment before you actually go back and troubleshoot those experiments, because I got a suspicion. Now, the way he's done that, obviously he's put the glucose sensor in the beaker and he's adding in glucose periodically, and the signal is stepping up quite nicely. When you've got that figured, then it's time to troubleshoot what you've actually got. I mean, we don't just do this once or twice, we're doing this all the time. So I've got a couple of links that will hopefully help you a little bit. Do I have anything else to say on that? Oh, I haven't actually put it in here. No, I haven't, and I'm sorry about that. Right, glucose plus oxygen in the presence of glucose oxidase reacts to give you hydrogen peroxide. When you're passing that much current, there's not enough oxygen in that solution to really keep up with that glucose oxidase demand. You should be oxygen limited. So I believe you're passing so much current, you're consuming so much glucose, the enzyme's working like crazy, but there's not enough oxygen in there to really keep up with that current. I have a super strong suspicion that the currents you're seeing are not the generation of hydrogen peroxide and the oxidation of hydrogen peroxide. I think they may be, sometimes with these kind of gold needles, there's some other metal involved that's actually corroding underneath those gold. I'm really surprised I didn't actually put a certain slide in there, but that said, maybe come to our wearables webinar. We may dig into that. You may have already been in there, for I apologize. Question number 4 is an important one. So somebody's thinking about adopting some of our screen printed electrodes, and which I'm really happy. It's probably worth saying, even if you're a reseller, it's probably worth encouraging your clients to actually attend or just be in contact with ZP, because we're pretty good on the technical support, and it's quite deep. So the question is, are screen printed electrodes, or are disposable screen printed electrodes, let's say, disposable or not? So there's been a lot of conversation this evening about ferricyanide. If you do simple experiments like ferricyanide, yeah, you can reuse the screen printed electrodes. You know, so I can take one of these, you can put a drop on there, you can actually reuse it. One thing I will say, you know, you'll have people who've kind of bent them and twisted them and broken them. No, at that point they're not reusable. You know, so you've got to be a little bit careful with that, especially if people are using them with scientists who are kind of a little bit rough with things, let's say. So that would be one problem. Sometimes this is a different cyclic voltammetry. What's the daisy? A different cyclic voltammetry experiment. In this particular cyclic voltammetry, it's not a simple oxidation and reduction of ferricyanide. We're actually oxidizing an organic molecule, and yeah, sure, you know, it works really well. But just play that a bit more. But in this reduction, the reduction material irreversibly binds to the surface of the electrode. So the next time you try to use this screen printed electrode, it's actually that you'll see a peak in a minute. It's this material is irreversibly bound. So in that case, yes, the answer to your question is, can you reuse ZP Hypervalue screen printed electrodes? Yes, you can. If it's something like ferricyanide in pH 7.4. But if you sometimes do an experiment where the material is organic and the organic material, or the molecule is organic, it may polymerize, it may coat the surface, at which point you can't reuse them because it's irreversibly bound. So the answer to your question is, it depends. And also, you know, if people are just going to treat things roughly like this, then obviously they're not reusable at that point. So the answer to your question is, if it's ferricyanide and it's a simple experiment, it should be fine. If they start, you know, and that's the whole thing about, you know, R&D, if they start using molecules that I haven't otherwise envisaged, in this case, this particular molecule on the right hand side, there's a, you know, the experiment works, but in doing that, the electrode gets modified by the molecule and you can't reuse the electrode. And that's the situation, if I can put it that way. Question number 5. This is an interesting one. Somebody's made a quite simple chemiresistor. They've really got 2 wires on a sort of PCB board, and they've sort of drop cast an ink that they've made themselves. This tetracosane and carbon powder. I meant to reference this paper, so I apologize to the authors of this. I genuinely meant to reference this. The first thing I want to say is they don't detail too much about the tetracosane and the carbon powder. They don't really detail heavily how they do that. So there's not enough information there for really anyone to just directly follow the paper. If anything, you'd have to kind of do trial and error yourself. But that said, 2 conductive wires, a conductive ink between them. If ZP was to go in to do this, actually I would use our Hypervalue carbon electrode, because essentially you can then drop cast that ink here. I didn't quite mean to touch this electrode here, because I was basically just, if you really look at this, I've got a conductive track here and I've got a conductive track here. So if you just drop cast between the 2 of them, you could then make a resistance measurement from here to here to here to here. If you made a resistance measurement there, then that would work in the same way that the paper is doing. The paper's just got a very, I don't want to call it crude, but it's quite a crude way of fabricating a sensor. It's not easy to scale that. You know, you kind of have to get all those PCBs and you have to do all that little soldering, when they could have used the screen printed electrode. Or you could also just drop cast in a similar place and use that electrode and that electrode. Again, I shouldn't have quite crept onto that electrode. So the quick answer is you can replicate that paper. Nobody's at this outside of those authors quite knows what that formulation is. That has to be probably trial and error, or maybe ask the original authors. And then you can drop cast either onto those 2 electrodes, which means you would make contact here and here, or you could drop cast and make contact here and here. So the quick answer is, if I was to repeat this, I would actually do it on the screen printed electrodes like I have indicated. It's not worth engaging a third party like Zimmer Peacock to make you a bespoke electrode at this point. You have to go, you basically have to try and replicate that paper by trying some of these experiments yourself. I don't think I put a link in, but you really need to get a good connector from Zimmer and Peacock. It's really important. Otherwise, you will have a resistance. Part of your signal is all about resistance. If you don't make good electrical contact with that piece, then part of your signal will be due to the resistance between the electrical contacts and the screen printed electrode. So it's really important to get a screen printed electrode from ZP. One of the things I'd say about this paper is they do not put raw signal in the paper. I have read the paper. They don't put raw signal in it. They put an abstraction or an extraction from the raw signal. But here they talk about sensor peak output. So, you know, there's an output, but that is not the raw signal. That is a processed raw signal, and it says time to peak. Again, it's not a raw signal. It's an extraction from raw signal. So you haven't seen the raw signal, and I haven't seen the raw signal. So how good this really works is not evident in that paper. These are extractions from raw signal. So I think my answer to your question is the Hypervalue carbon electrode with a ZP connector is what you need, but you need to do some science in a lab, actually trying out those formulations, and just know that that paper that you're following doesn't have the raw signal in it. It has extractions of the raw signal, but not the raw signal itself. Question number 6. A long-time colleague of the company is interested in purines, pH, hormones, and nitrate. And ZP, we do have this Sensi-All platform. Now, this is also a potentiostat, but it's both an analyte. It can detect analytes. So in this particular case, the person's interested in purines, which I don't have a QR code for, but purines is something, this instrument is being used at the moment in a clinical trial in the UK for screening stroke patients. When they enter the emergency room, they're screening them on purine, because I think when you have a stroke, you can have what's called stroke mimics, and you can have people who are generally having stroke. A stroke mimic could be somebody who's actually drunk, but a genuine stroke could be purines. They think maybe one of the biosensors for that. So purines is on the platform. Testosterone they're also interested in, nitrate they're also interested in, and pH are also interested in. I should actually just change screens real quick actually. So if you come to us and you want to do one of the hormones and it's testosterone, then by scanning the QR code I can do testosterone. If I scan that was potassium, I didn't want potassium, I wanted pH. if I scan the, sorry, and I keep doing that slightly off screen, but that's pH. And then the other one you were interested in was nitrate. And I can scan the nitrate one and also get to nitrate as well. So what I want to do is a technology integrated stack. So I need to change screens. What you can do is take the sensors, take the app. Yeah, we've got this technology, it all works together. I know you've been to one of our webinars already, so it's not really the webinar to do this in, but actually at ZP we have a potentiostat which can either do things like amperometry, open circuit potentiometry, impedance spectroscopy, linear sweep voltammetry, cyclic voltammetry, square wave voltammetry, and it's also got something called a data pipe in it. What it means is we send the data to the cloud, we put the raw signal through a series of filters or pre-processing, processing, turn it into information, and actually send a concentration back to the phone. So it's quite a technology stack, and it's the only potentiostat where you can actually end up with concentration of glucose as opposed to just current, which is, you know, some of the data that we've seen this evening. So sensor goes on jig, sample goes on sensor, app knows what to do through a series of QR codes, app tells meter what to do, meter gives data back to app, it could be cyclic voltammetry, that gets sent to a system called Julie. I think Julie is not a simple thing to do. We've been working on Julie for 10 years. Julie is a cloud system optimized, or a cloud data management system optimized for electrochemical data that can receive data like EIS, impedance spectroscopy, or cyclic voltammetry. And in there you can actually do what's called pre-processing, processing, turn it into information, i.e. concentration, which is information, and actually send it back to the app as well. It's the only potentiostat system that can do it like this. If you're interested, scan this QR code. If you're interested, scan this QR code depending on whether you've got an Apple or an iOS. If you do this, you probably don't have an account, so click don't have an account. You will essentially create yourself a set of credentials. It's really important to realize that the app is actually a, how do I put this, is a conduit to the cloud system. So you'll end up creating a username, like you'll have your email and your password, but also understand that when you do something in the app, it automatically saves to the cloud. So if you're doing cyclic voltammetry, the cyclic voltammetry is automatically saved to the cloud. If you're doing EIS, it's automatically saved to the cloud. If you're doing testosterone, it's automatically saved to the cloud. So these, you'll be able to log then in using those credentials into this cloud system and find your raw data all saved up in the cloud. So these two things are synchronized as long as you use the same credentials. Well, the credentials that you use for the app, you can log into Julie, and then you'll find out that actually you have an account in Julie at the same time. When you do log in, it's going to actually try to access your the QR reader on your phone. So in fact, I just opened this up now, so there we are. You can see that it's got the QR reader. I'll just do square wave voltammetry again. Yeah. So now I can actually do square wave voltammetry. So I'm just saying that the things that you're interested in fact, all of them already exist. It's just as crude as purchasing, really. But if you're somebody else who's like asking about screen printed electrodes, you also know this is a full potentiostat as well. So we have both potentiostat mode and analyte modes. You can scan all these QR codes if you end up installing the app on your phone, and you'll soon see that you've actually, if as long as you've got the hardware, then you're able to get into all these things and start playing with all the settings. Maybe if you're watching the video, you should actually pause me as I went a bit quick. There's impedance spectroscopy as well. But because we've got this data pipe built into this, you can actually set up amperometry experiments and then, for example, turn them into glucose signals. So it's a very powerful way of, and I realized something, an academic told me the other day, that they can actually now publish in more impactful journals, because actually they don't have to finish their scientific paper with a kind of calibration curve and some raw signal. They can actually finish it with, and we programmed this into the Sensi-All platform, and we were able to actually turn that into potassium concentration, pH concentration, etc. So you can go beyond the normal technology readiness level number 3, where most papers finish, and actually take it on and make it much more of a product like paper. Sorry, question number 7. This is a tricky one. I have been thinking about this for several days. Measuring ethanol is fine. Measuring ethanol in a 96 plate format, which we do have, is challenging, and doing it where you've got material in there, biological material that would just love to coat the surface, is quite challenging. So the quick answer is, if you were trying to do it on our Sense It All platform, so I'll just quickly so this is Sense It All. So let's say I was following a fermentation. I should have grabbed some pipettes. I would find that much easier conversation to have with you, because we could take a drop, put it on there, measure the alcohol using the app, get a result, and we're done. And then the sensor's disposed of. That's an easier application. The challenge of doing that 96 times in parallel is much tougher. And if you want to stop, if you're worried about, if I'm doing an alcohol measurement, that measurement would be over in 2 minutes. So I'm not so concerned about fouling or biofouling at that point. If you're trying to do this inside a fermentation or bioreactor, then you are going to have fouling issues. So the fouling, trying to have anti-fouling is more challenging. Now at ZP we do have a whole range of biosensors, and we do have experience, quite a lot of experience actually on the alcohol sensor, but not in a 96 well format. And if you change the rules on us and said, all right, well, I'll put that biosensor straight in that bioreactor, I would also find that quite challenging because of the continuous mode of operation. My advice is, if you're commercial and you're thinking about making a commercial product, you've got continuous monitoring, and you've got discrete testing or spot testing, where you just take a sample, get a result, done. Honestly, have a roadmap where you actually just do the discrete spot testing before you get into the complexity of microtiter plates, or before you get into the complexity of continuous monitoring. I mean, this is a continuous monitoring system. You could argue that this is more challenging than your bioreactor, or rather measuring alcohol maybe in a fermentation, but it's still a challenge. And I would generally argue that if you were trying to do 96 well alcohol sensing, you were talking about hundreds of thousands of dollars worth of development just to get to a prototype phase. So my advice is, come to our Sense It All webinar actually and have a look at this platform where you can do discrete measurement. Question number 9, I am interested, so this is they're talking here about a third-party potentiostat. It's not a ZP potentiostat, but I think they've either got it or they're going to buy it. If you haven't bought it, please strongly consider our potentiostat first, because I think one of the problems you may have with the potentiostat that you're thinking about buying is it might have a compliance potential or compliance voltage limitation. The compliance voltage is not talked about that much these days. Compliance voltage is being talked about more these days. Compliance voltage is this, that you tell your working electrode, I would like to hold that working electrode at 650 millivolts, for example. What the potentiostat is trying to do then is applying a potential between the working and counter, so that a current is passing, so that in fact the potential at the working reference is 650 millivolts. So you kind of dial up the potential you want between the working and reference, and the potentiostat is actually applying a potential between the working and counter and trying to pass a current in order that you get the potential that you're looking for between the working and reference. The potential between the counter and working is called the compliance voltage. This didn't used to be a problem, but potentiostats have become smaller, lower power, and I know what you're trying to do. You're trying to do lateral flow strips, or trying to do immunoassays, let's say. And I think the potentiostat that you're working with may actually have a compliance voltage issue. But that said, I think, first of all, our screen printed electrodes are compatible with that potentiostat, but I can't support it if you run into problems. That is a problem, because in the end, is the problem with the potentiostat, which is always the problem with our screen printed electrodes. I think you will actually see that I've been talking for about too long, is the quick answer. 50 minutes. So at ZP we do have a lot of experience about screen printed electrodes, and lots and lots of discussion this evening. So we have solved our screen printed electrodes, we've optimized them on distance. What I mean by that is our electrodes are are separated but close enough to one another to sort of function quite well. We've got the area of our electrodes correctly. Somebody was passing a massive amounts of currents in some of the earlier experiments I was describing. Sometimes the working electrode areas are actually just too big, but we got that right. We've got the ratio right. This has really dropped off in the world of electrochemistry, especially screen printed electrodes. People have forgotten about the ratio between the working and counter. If you've never considered the ratio between working and counter, it's probably worth looking at a YouTube video that I've done on compliance voltage, and also one on IR drop as well. Materials. So this one electrode actually has a really good material for the counter electrode, which really helps. That's our Hypervalue carbon electrode, by the way. It really helps with the compliance voltage issues that I'm sort of flagging up. Solution as well. When you're using screen printed electrodes and you're asking questions about sensitivity, background signal, do you know so much of this is actually also part of the way you develop the assay and the solution you use? I think it's interesting actually, because sometimes people think that all the problem lies with the screen printed electrode, but you've got to kind of have a holistic view on things. So when I say a holistic view, I mean, you know, this is a holistic view. This is a ZP potentiostat, so we somewhat understand that. Well, we definitely understand that. This is a ZP screen printed electrodes, so we definitely understand that. This is a ZP app, which sends data to a ZP cloud. So in some ways, when people are on our platform, I find it much easier. Of course, once you start saying, well, I'm going to use you in conjunction with X, Y, and Z, I don't necessarily understand the other two parts. I can only talk for what we understand. But that said, you may be using a third-party potentiostat, and that is your prerogative. Just say it could be hard for me to necessarily support you. We've also optimized that, in fact, we pass appropriate current. So I have said it earlier on that some of the experiments we've been looking at this evening, there's a lot of current passing through those experiments. And when you're doing analysis means that you're analyzing the system. High current means you're doing synthesis upon the system. So there is actually a subtlety in the world of analytical electrochemistry. Too much current means too much synthesis. You're not doing analysis, you're doing synthesis. It's not philosophical. It's something I've definitely come across where people have made sensors that are just too active and they end up disturbing the thing that they're trying to sense. So in summary, you're very welcome to use the potentiostat you are, but I would super encourage you to use our screen printed electrodes. They will work with your potentiostat. Of course, I am biased. My name is Martin Peacock, one of the founders of ZP, would prefer that you use, of course, the ZP potentiostat, but that is also your prerogative as well. It's just going to be harder to support if you have problems later on. So in summary, cyclic voltammetry screen printed electrodes, I genuinely believe it's ferricyanide. It is a reversible system. I have given you quite a harsh way of cleaning that surface of that electrode. I hope it works rather. I've never done it on that screen printed electrode, so you may lose a few screen printed electrodes trying it. We have done it on our screen printed electrodes. Question number 2. This is going to be an ongoing question, because actually I think that you do have reproducibility. I think what you're having problems is anchoring macromolecules onto the surface of that gold electrode. Question number 3, CGM. You have to kind of roll this back a bit and actually get that classic staircase response before you then move forward again. But I got a suspicion those microneedles are just passing so much current. You've got a corrosion, I think, is what's going on there. And if you were passing that much current, you're turning over a lot of glucose into hydrogen peroxide. I just don't think there's enough oxygen flux in that system to actually produce that much hydrogen peroxide per second. Can our carbon electrodes be reused? Yes, they could. Simple experiments like ferricyanide in a buffer, strong acids, strong bases, organic solvents, organic molecules that love to stick or stick to the surfaces. That would stop them being not reproducible, but reusable. ZP can make a chemiresistor. That paper has a little bit of a flaw in it, that they don't describe how they formulated that ink, but that can be worked out, to be honest with you. You know, an afternoon in the lab could probably sort that out. But they don't show raw signal on that, so you have to take that risk of get some screen printed electrodes and connectors of ZP and drop cast in the way that I've maybe described, and actually sort of redo the paper, but do it on a substrate that's probably more manufacturable. And we can definitely do purines, pH, hormones, and nitrate. In fact, we can just do it on this particular platform. The whole point about this particular platform actually is that it allows people to go from TRL3, which is just lab testing, to much higher technology readiness levels much quicker than normal. It's a big lift to try and do ethanol detection in 96 wells, and maybe having to work with let's say biofouling or coatings to stop biofouling. I would honestly, if you're in a commercial mindset, I would honestly thinking about doing discrete testing on a platform like this, with a view and a roadmap to do continuous monitoring. But if you're commercial, I would actually go for the market for a discrete test before I went for a continuous test. And if you want to do 96 wells, I think you're talking about hundreds of thousands at least of investment. I put number 8 here, yeah. Number 8, perfectly glad that you're trying to do viral detection on screen printed electrodes. We have actually done this, it does work. Particular potentiostat you have may have a few problems, but I'm also biased. I prefer that you used our potentiostat. Our screen printed electrodes do have the right connector for the potentiostat that you're interested in. What I mean by that is these pads here are 2.54 millimeters apart, which will mean they work. But if you run into problems either through connection or you run into problems just through science, it is going to be harder, if not impossible, for us to otherwise support you. If you've got any questions on ZP, don't hesitate to reach out to us. It's getting quite late here, so I wish everyone a either good weekend or good rest of the week. Okay, thanks very much.